Welcome back to Statics 1. Today, we're going to be talking about scalars and vector quantities. We're going to talk about some simple operations that are performed on vectors, including multiplication by scalars. And then we're going to talk about how to add vectors using graphical techniques called the triangle rule and the parallelogram rule. Okay, so what is this vector? A vector quantity is essentially, let me write it here, vectors. It's essentially something that has a magnitude and a direction. All right, so magnitude means like how much there is, and it has some direction. All right, and this has particular relevance to our class in three types of vectors that we're going to see. The first of which is a force vector, which is, as it implies, the name implies, it's essentially a force that's going to be, has a magnitude, obviously, and then a particular direction. The magnitude would be in units of, like newtons or pounds, which are our force units. The other types of vectors, we're going to talk about them later in the term, is something called a position vector, which describes the location of a point relative to some other point. It would have units of either meters or feet. Let me write that here. This one have newtons or pounds. Right, our force vector would have those kind of units. Position would have units of either meters or feet. And the third type of vector is a moment vector. And a moment is essentially a force that's causing a rotation. So a moment, and this is frequently something that's confusing to students, but the direction of the moment is perpendicular to the direction of the rotation. So we have rotation like in the plane of the board. Then the moment would be either coming out of the board or into the board. And we'll talk later in the term about like what is a positive moment, what is a negative moment. So the moments have units of, they're compound units. They're either Newton meters or feet pounds. So these are our vector quantities. We also need to define certain scalar quantities. So a scalar quantity is essentially just a magnitude. So for example, it has just a magnitude, no direction. So for example, we could have something like mass. Unlike like a weight force, which has the direction obviously in the direction of the center of the earth, like for gravitation caused by the pull of the masses between the object and the planet itself. Mass, length, time, as long as we only think of time as going forward. Mass, length, time, other sort of quantities that are very similar to those that are all scalar quantities. So that's the definition of a scalar and a vector. Okay, now in a minute we're going to talk about how to represent those graphically, particularly how to represent vectors graphically, then how to do the scalar operations that I was referring to. So now let's discuss the graphical representation of vectors. So a vector is essentially drawn graphically as an arrow with a shaft. So you have a shaft, we always draw a vector. In the book, you're going to hear sometimes they talk about the tail and the head of these vectors. This is the tail, and sometimes I get it mixed up. This is the head. And what you always see is an arrow on the vector. The arrow tells you the direction that the vector is pointed at, and the length of the vector shaft is essentially proportional to the magnitude of the vector. So if I were to draw a second vector right here, and I'll draw in the same direction, but it has half the length, then this vector, essentially the magnitude of this vector, essentially half the magnitude of that larger vector. All right, so we always draw, when we're doing, when we're Doing our homeworks, we're always going to use a small arrow over a letter to indicate that a quantity is a vector. So you're going to see it like that. In the textbook, you'll always see that they won't show the arrow, but they'll represent the letter using like a bold font. And then they'll use a italic font to show the magnitude of the vector. So this would be, if this was f was referring to this larger vector, we would have the magnitude of the vector represented using just a simple letter. So in your homeworks or in test problems, you always just use a simple letter to describe the magnitude. So this is a vector, and this is the magnitude of that vector. Okay, and this is a scalar quantity. Remember we talked last time about vector quantities, scalar quantities. So this is in fact a scalar quantity. All right, so I'm going to erase this, and then we're going to talk about how to add vectors. Now we're going to talk about the parallelogram law for adding vectors. It's essentially the same. The concepts are essentially the same as doing the triangle rule. So again, let's say we have two vectors. This is vector 1, which you represent as f1 with a bar on it, showing it's a vector. And we have f2 over here, again, a vector with a bar on it. And now we're going to use the parallelogram rule. And what you're doing with the parallelogram rule is you're going to draw a parallelogram, and then the resultant vector goes from the one corner, basically back here where the tails are touching, to the point where the other point of our parallelogram, which I'm going to show you where that is in a minute. So to do this, what color should I use? I'll use green. What we're going to do is we're going to draw a line parallel to F1 that starts at the head of my F2 vector. Let's see if I can draw this parallel. Whoop, didn't do that very well. Let me try again. I think that looks, well, what do you think? Okay, not bad. Let me erase it. Try again. One more time. If you have like engineering paper, you're probably going to have better success. Let's try one more time. All right, I like that one better. You just draw it full length, doesn't matter the length. Okay, so the point is that this line is parallel to our F1 vector. Then I'm going to draw another line starting at the tail of F1, starting at the head of F1, and it's going to be parallel to my F2 vector. So here we go. Let's see if I can get this one right. Oh, not bad. I like that one better. And our resultant vector is going to go from the tail of our two vectors to the other side of our parallelogram, like that. I need a new red marker, dry erase marker. So that is our value. And remember that R is the sum of these two vectors. So we're taking the sum of F1, F2, and that's equal to our R. And remember, we're using R because R stands for resultant vector. This is the resultant force from the application of these two individual force vectors. All right, so we're going to erase this now, and then I'm going to talk about multiplying scalars times a vector quantities, and how to do that graphically. Okay, so we talked about how to add vectors. Now I want to talk about multiplying scalar quantities times vector quantities. So we're going to talk about multiplication of scalars and vectors. All right, so imagine we have a vector we're going to call f, and it starts, remember again, this is the tail, the head, the direction is, and the arrow is telling you essentially whether it's going in this direction or the other direction. And we can multiply these by scalar quantities, and essentially when you do so, if the scalar quantity is greater than 1, it's going to be stretching the vector. The resultant vector will be stretched, but the direction will not change. If you multiply it by a scalar quantity less than 0, we're going to have essentially reversing the direction, and the vectors will be off in this direction. So let me show you a few examples. So imagine that you're going to multiply this f quantity by 3. So we're going to say f2 is equal to 3 times f. And notice that the resultant of this, we're multiplying a scalar times a vector, and the resultant is another vector. So what you're going to end up with is a vector in the same direction, but it's going to have 3 times the length. See if we can do this. 1, 2, 3, somewhere out here. Okay, so this is my f. Here's my f2 vector. It's 3 times the length, more or less. I haven't drawn it exactly right, but the direction is unchanged, and the magnitude of my new f2 vector is going to have 3 times the magnitude of my f vector. Okay, now what would happen if we were to multiply this by a -1 value? And I'll put this over here, see if I'm still on the page. Yep. So I'm going to say f3 equals -1 times f. All right, so the magnitude is not changed because the absolute value of the scalar quantity is 1, so it's not going to change the magnitude. However, the direction is going to be reversed. So I'm going to draw we'll try and do this better. Here's my new vector. Notice that the direction has been reversed. However, the length represented by the vector, or the length which represents the magnitude of the vector, is essentially unchanged. This is my f3 vector. Okay, so that's showing how to multiply scalars times vectors. We can actually, and we're going to talk about this later in the term, but I want to introduce the concept, multiplying vector quantities. So you can multiply and there's actually 2 ways of doing it. There's one way we call it dot product, and there's another way we call a cross product. And I'll just introduce the term so later in the term when we actually deal with these dot products and cross products, you at least have some recollection of that. So what would happen is, I'll say it this way. Let's say we're going to take vector 1, vector 2, and we're going to do a cross product, and these are vectors. It turns out the cross product ends up with, I'll use C. When you take the cross product, 2 vectors, you come out with a vector. That's what you say is V1 cross V2. And if you do a dot product, which is represented using, not surprisingly, a dot, you're going to end up with a, not a vector, but you end up with a scalar quantity. Okay, so we're going to be dealing with these later in the term, but I just wanted to let you know that you can multiply vectors not only by scalars, but you can actually multiply vectors by other vectors. And they actually have some very interesting properties that we're going to be dealing with later in the term. All I want to talk about right now, and I will see you in class.